Let's prove an even more interesting claim about graphs. So let G be a graph where every vertex has degree less than or equal to k. Then the claim is that G is k plus 1 colorable. So again, G is a graph. It could have many vertices. We're not saying anything about how many vertices it has, but we are saying that every vertex has degree less than or equal to k. And in that case, we're saying that G is k plus 1 colorable. So by the way, a graph where each vertex has degree less than or equal to k, we would say that the max degree of G is less than or equal to k. The proof is by induction. That's why we've been doing all these proofs by induction. Now, in all of our previous proofs by induction, it's been pretty obvious or pretty simple to write down what the induction hypothesis to be, what your predicate should be. In this case, if we do the obvious thing, it won't work. And that's what's really interesting. So let me show you why the obvious approach for writing down the predicate doesn't work here. So what would you do? Here's how you would start a proof by induction. You would say P of k is just what I've written above. Any graph G with max degree at most k is k plus 1 colorable. Okay, that's how you would start to write your predicate. Seems reasonable. I myself would try and do it this way. Okay, and then let's try P of 0. That could be our base case. P of 0 is any graph with max degree less than or equal to 0 is 1 colorable. That means you're given a graph, all of the degrees are 0, and you want to show it's 1 colorable. Well, if your graph has degree 0 on every vertex, it means your graph just looks like this. There are no edges at all. And so yes, it's 1 colorable. You can assign just 1 color to every one of these vertices, and it will be 1 colorable because there are no edges. So the base case is not a problem. Now we need to show that for all k, P of k implies P of k plus 1. Okay. Let me move this up so you can see P of k. So we assume P of k is true. We need to prove P of k plus 1 is true. So what is P of k plus 1? It says any graph G with max degree less than or equal to k plus 1 is k plus 2 colorable. Okay, so let G have max degree k plus 1, need to show it is k plus 2 colorable. My step 3 would be, since G has max degree k plus 1, then there has to be a vertex with degree k plus 1. So let V be a vertex of degree k plus 1. Okay, like I said, G has max degree k plus 1. We have to show it's k plus 2 colorable, so let's let V be a vertex of degree k plus 1. That's a valid step. Then I'm going to remove V from G and all of its edges. A slightly odd step, but it's common when you're doing induction on graphs. You take your graph, you take your vertex v, you remove it, and you remove all the edges that connect v to g. We're left with g prime. And when you're left with g prime, what you'd like to do is to apply the inductive hypothesis to g prime. You'd like to say, okay, I've removed v from g. Now I have this graph g prime. Its maximum degree has gone down because I've removed v from it, and so now I can apply the inductive hypothesis to g prime. The problem is that even though you've removed v from g, there could be many vertices that have degree k plus 1. So just because you've removed one vertex from g doesn't mean that you've decreased the degree, the maximum degree in g prime. I mean, if I have two vertices in g that have degree 10, and I remove one of them, g prime still has degree 10. So the inductive hypothesis, which talks only about graphs that have max degree k, it doesn't necessarily apply to g prime because the maximum degree hasn't necessarily gone down. And so we can't directly apply the inductive hypothesis to g prime. So let me show you how a proper proof should go. So I'm going to use the following induction hypothesis. P of n will be the statement that any graph G with n vertices can be colored using max degree of G plus 1 colors. So notice if we could prove that for all n, P of n is true, then we would have given a proof to the claim. We would show that for any graph with n vertices, you look at its maximum degree, you add 1 to that, and you can use that many colors to validly color the graph. So I guess I should put, I mean colored, but I mean validly colored here, of course. So what we'd like to do is prove for all n P of n. Notice last time we had P of k, we were doing induction on the degree. Here we're doing induction on the number of vertices. So first I want to give you a little intuition as to how the proof will go, and then I'll write down the actual formal proof. So remember, we need to prove that for all n, we want to prove for all n P of n. When you do a proof by induction, you need to show that for all n, P of n implies P of n plus 1. So we need to assume P of n is true, and then prove P of n plus 1 is true. What is P of n plus 1? Well, it's just the above. Any graph G with n plus 1 vertices can be validly colored with max degree of G plus 1 colors. So we need to prove that P of n plus 1 is true, assuming P of n is true. Okay, so here's the high-level idea, and then we'll write down a more formal proof. So I'm going to let G be a graph with n plus 1 vertices. Remember, this is what we need to validly cover, because we need to prove that P of n plus 1 is true. So, you know, we have some graph. It has n plus 1 vertices. I don't know what it looks like. It's totally arbitrary. So what I'm going to do is I'm going to pick some vertex in the graph. Let's say this one. It's an arbitrary vertex. I'll color it in black here. And I'm going to call it V. Okay, this is the letter V. So this is my vertex, the one I've colored in black. And what I'm going to do is I'm going to remove it. I'm going to remove V from the graph G. Okay, so I'm going to rip it out. what happens when I rip out that vertex? I'll be left with a new graph, which I'll try and draw here. Called G prime. So this was G. This graph is G prime. And notice that G prime is G, but I've taken out this vertex here. So when you take out a vertex, you remove all the edges that were connected to this vertex. So now I have this graph G prime. Notice that G prime has n vertices. What's its maximum degree? It's not clear. It could be the same as G. There could be many, maybe this wasn't the max degree vertex that we pulled out. But we do know that it has n vertices. It has one fewer vertices. So now, since it has n vertices, I can apply P of n, and I can color it using max degree of G prime plus 1 colors. Right? That's what the inductive hypothesis tells me. But max degree of G prime plus 1 is at most max degree G plus 1, right? G prime has fewer vertices than G, and they're the same, we just removed one vertex, so the max degree of G prime can't be any bigger than the max degree of G. So by induction, we're going to color it then using at most max degree of G plus 1 colors. So we've colored G prime. Okay, so by induction, that means there's some coloring of G prime. Maybe we color some others red. Who knows what the actual coloring looks like. Maybe we have to color this one black. All we know is that we only use max degree of G plus 1 colors. Now what did we need to prove? We needed to prove that G could be colored using max degree of G plus 1 colors. So we need to color this graph. And now we have a coloring of this graph. So what do? Well, we need to reinsert V right here. And we need to reinsert V's edges. And now we have to color V. Well, in the absolute worst case, how many colors are going to border V? Well, how many neighbors could V have? V has at most max degree of G neighbors, right? We know that V has at most max degree of G neighbors by definition of maximum degree. Every vertex in G has at most max degree of G neighbors. That's the definition of the maximum degree. So it might have this many different colors surrounding it, in which case we need to use a new color for V. But that's okay, we're allowed to use max degree G plus 1 colors. So even if there are max degree G different colors surrounding V, we can still use that one remaining color to color V with. And then we will have used max degree of G plus 1 colors, and that's exactly what we wanted to prove. So I'll try and write down the proof in a bit more formal notation right now, although if you've understood this, then you might want to try writing it more formally by yourself. Okay, so let me try and show you how a more formal proof would be written. So remember, we want to prove that for any graph G with n vertices, it can be validly covered using max degree of G plus 1 colors. And so we want to show for all n, P of n is true. And we know in a proof by induction, you actually need to show that for all n, P of n implies P of n plus 1. Okay? So, P of 1, the base case, is very simple. I'll let you check that on your own. Then we need to assume, as usual, P of n and conclude P of n plus 1. We need to prove that P of n plus 1 is true using P of n. So, I guess that's step 1. Step 2, let G be an arbitrary graph with n plus 1 vertices. Let V be an arbitrary vertex of G. Remove V from G to obtain G prime. By the induction hypothesis, we can color G prime using max degree of G prime plus 1 colors. And we know that since we've removed a vertex from G to get G prime, that max degree of G prime plus 1 is less than or equal to max degree of G plus 1. Okay, so we can think that we've colored G prime using at most max degree of G plus 1 colors. So now we must color V to complete the coloring of G. Remember, we've colored G prime, but we still need to color G. So V has at most max degree of G neighbors. When we're putting back in V, we need to assign it a color. It has at most max degree of G neighbors, so there's one color left over to assign to V. The coloring is valid because G prime is validly colored, and now V is validly colored. Why is V validly colored? Well, as I already said, it has max degree of G neighbors, so even if they all have different colors, there's still one left over to assign V to make it a different color than all of its neighbors. So therefore, G is now validly colored. And we've used still max degree of G plus 1 colors. Therefore, P of n plus 1 is true. And this completes the proof by induction.